What is going on, guys? Welcome to our last lecture for this chapter of eigenvalues and eigenvectors. Most importantly, the last lecture of linear algebra. Oh my god, we finally did it. You guys finally did it. This is the last lecture with the last set of examples for you guys to watch, and after that you can say that you've taken linear algebra. But even though this is the last lecture, this kind of be a little bit a long one, sort of. Let's just make sure that it's not that long. So let's get right into it. So this last lecture will be looking at more with the eigenvalues, more specifically complex and defective eigenvalues. And before I start getting into what those are, again, we're just going to do a quick little review on finding the eigenvalues. And so the first thing to find the eigenvalues is to find the characteristic equation, use it, and then you find those roots. Those roots will be the eigenvalues. And so far, up until now, every characteristic equation had real eigenvalues. And that's not always the case. And we know when it comes with polynomials and roots, we know that they can have multiple types of roots, whether they're real, complex, or just one. And like I said, we can have complex eigenvalues because the characteristic equations, there are some, according to the fundamental theorem of algebra, we can have complex solutions. And so how do we deal with these complex solutions? Well, they even with the complex eigenvalues, if they are distinct, we can still get their corresponding eigenvectors. So it's nothing new. It's the same thing. There's a little catch to that. Obviously, the first one is that we'll have complex value solutions, but if the entries of the matrix that we are finding the eigenvalues for contain real numbers, so that means it doesn't have a complex number, so anything that involves the square root of -1, then these complex eigenvalues will come in complex conjugate pairs. And if you remember in, I believe, Algebra 2, complex conjugate pairs is basically their plus or minus. So if you have a complex number, say 3 plus 2i, its complex conjugate will be 3 minus 2i. And why is that? Why is this true? Well, it's through the quadratic equation. So you remember the quadratic equation is equal to negative b plus or minus, which is where the conjugate comes from, the square root of b squared minus 4ac all over 2a. That plus or minus is where our complex conjugate comes from. And like I mentioned, even though we have like a 3x3 or 4x4 matrix, we can get solutions in terms of just using the quadratic equation. And that pretty much means that for a 3x3, we'll have a linear function multiplied by a quadratic function. And then if we have like a 4x4, we'll have two quadratic functions multiplying each other. And so and that's why we use the quadratic equation, mostly because we know how to solve quadratic polynomials. and what's so special about these conjugate pairs? So because they come in complex conjugates or in conjugate pairs, what's so cool about them is when you find their eigenvectors, all you have to do is find the eigenvector for one of them. And what you essentially do is you find the eigenvector for both of them. In other words, the other eigenvalue. And I will show you an example like how do you find them. Obviously, you just do it as is, and then all you have to do is just take the complex conjugate of the eigenvector that you found, and that will go with the other eigenvalue. So now let's talk about defective eigenvalues, or eigenvalues, because there can be more than one. So in hindsight, defective means, not good. So that's That's what we're going to be talking about. And there's a reason why, in this case, why defective eigenvalues are not so good or not so nice. So an eigenvalue is said to be defective if the algebraic multiplicity is greater than the geometric multiplicity. So remember when we discussed about algebraic multiplicity and geometric multiplicity, and how the best case scenario is if the geometric is equal to the algebraic. This is the case when the algebraic is strictly greater than the geometric. And why is it defective? Well, the reason why it's called defective is because you can't create a diagonal matrix. So that means the matrix you are working with is not diagonalizable, which is not good. We like diagonalization. It makes our lives easier. And so within a defective eigenvalue, you're just kind of like scrambling to find a diagonalized matrix, which you really can't. And so the number of defective eigenvalues in a given matrix is simply calculated by taking the algebraic multiplicity and then subtracted by the geometric multiplicity. And even though they are defective, you can pretty much still find the missing eigenvector, so you can make it equal to the algebraic multiplicity. So remember, if the geometric and algebraic are not the same, then that means there are going to be missing eigenvectors when you plug in that eigenvalue to find the eigenvector. So let's say if you have a multiplicity of 2, but the geometric multiplicity is 1, then that means when you put in that eigenvalue into the matrix, you'll only be able to find one eigenvector. And so the other one's kind of like missing. It's lost. But we can still find them. And how do we find them? Well, let's do a quick little example for finding the eigenvector of a defective multiplicity of 2. So obviously the first thing you do is find your a minus lambda times I. So you plug in the eigenvalue into the matrix. And then what you do now is you're going to calculate a minus lambda I quantity square. So you're going to have to square the matrix, unfortunately. And now what you have to do is you have to find a non-zero solution that we will call V2. And this will be our column vector, such that the a minus lambda I quantity squared times that vector is equal to 0. But if you use that same column vector and multiply it by a minus lambda I, it does not give you a 0 column vector. And that non-zero vector v1 will also be an eigenvector. And so your v1 and v2 that you find will be your eigenvectors associated with lambda. So what we ended up doing is we took our first a minus lambda I. When we plugged it in and did row reduction, we saw that the rank is equal to, what is it? 0? No, the rank is equal to 1, so that means the nullity is equal to 1. So that means the geometric multiplicity is equal to 1. That means you can only find one eigenvector there. But if you square that matrix, you can find a vector such that that matrix squared is equal to, multiplied by that column vector is equal to 0. And then you use that same column vector to go back to the original matrix, and you get another vector. And those two will be your eigenvectors associated with lambda. A quick side note with this is the vectors that you find are the vectors that you must keep. There's no reducing or simplifying. So let's say you get a vector that's 6, 12. Do not by any means divide everything by 6, giving you 1, 2. That will be invalid, and that will not be an eigenvector. And so in general, what we have in overall when it comes with eigenvectors, we have generalized eigenvectors. And so if lambda is an eigenvalue of the matrix A, then the rank R generalized eigenvector associated with lambda is a vector that we'll call V, such that a minus lambda I quantity raised to the R times the vector V is equal to 0, but a minus lambda I quantity raised to the R minus 1 is not equal to 0. And so if R is equal to 1, then that means that V is an eigenvector associated to lambda. And this is what we call the original eigenvectors, or the ordinary vectors. Anything greater than 1 will be a generalized, but more on that later. So in terms of the last slide, V2 is a rank 2 generalized vector, but for V1, that will be the ordinary vector. And so for V2, that like I said, it's not an ordinary vector because its rank, or R, is greater than 2, and that would be a generalized eigenvector. So a quick little note is that all ordinary eigenvectors are generalized eigenvectors, but not all generalized eigenvectors are ordinary eigenvectors. And so higher multiplicity methods involve longer chains of generalized vectors. So what that pretty much means is, if we have a multiplicity of 3, and in our case from the last slide, we squared the matrix, it is possible that we end up having to multiply the matrix by itself again. In other words, raise the original matrix to the third power, and then see what we can get from that vector. However, the longest possible chain is usually d plus 1, where d is a number of defective eigenvalues. So if the eigenvalue of the defective eigenvalues is 3, then that means the longest chain that can possibly be there is 3 plus 1, which is 4. And obviously there can be cases where it's much less, but at most it will always be 1 more than the number of defective eigenvalues. And so now this brings us with the Jordan-Canonical Form, or the Jordan-Normal Form. So, what is this? Jordan, it's not Michael Jordan, and it is a very interesting matrix. For starters, it is a matrix. And so if the n by n matrix A has S linearly independent eigenvectors, then it is similar to a block diagonal matrix of Jordan-Canonical Form, such that J is equal to the matrix shown, where the main diagonals are Jordan blocks, that is K by K, and contains the size, or containing the eigenvalue. And so the size of the block corresponds to the length of the chain of generalized vectors. So if we have a chain 3, then your block is going to be a 3 by 3 Jordan block. If it's 1, then it's just going to be a 1 by 1, which is just the eigenvalue itself, and so on and so forth. If all the generalized eigenvectors are arranged as column vectors in a proper order, corresponding to the appearance of the Jordan block, this will result in a non-singular n by n matrix Q, such that J is equal to the inverse of Q times matrix A, which is the matrix that we are looking at, multiplied by Q. And this is what I would say is the closest thing we can get to diagonalizing a matrix that has defective eigenvalues. And so of course, it's not going to be a perfect main diagonal of values with zeros all around, but it's going to be really close, as you'll see in the examples. And so that's pretty much it for this lecture. Again, this is the last lecture. Congratulations to you all to sticking through this, and of course I think I have 3 examples on these. 3 examples on this lecture, and I'm pretty sure that'll be all, and we'll be done. However, this is just the beginning of this lecture, mostly because this becomes very practical when you're working with ordinary differential equations. So what that means is, when you get to differential equations, we're going to still use linear algebra, but it's obviously going to go in the ODE playlist and webpage, so I'll see you guys there. But other than that, thank you very much. Thank you guys for watching, and I'll see you guys in the Blackboard.